Hello class, today we're going to take some notes on applying the actual properties of logs. On Friday when you guys were here, you guys completed this worksheet front and back. Most of us got at least to this point or further. Okay, so now we're going to apply the rules and the patterns that we learned in each of those boxes. Okay, so we're going to apply those rules here for these notes. So go ahead and put your name and class period above example 4. And this is homework number 4. And you're going to get an easy 100 if you take the notes. Do not mute me. Do not fast forward. Just pay attention to the rules, okay? Pay attention to the video. Okay, so we have properties of logs. We have if you're multiplying two log functions together, same thing as adding them together. You multiply m times n. If you're dividing two log functions together, it's actually the same thing as subtracting them. Okay? So product is the same as addition, and division is the same thing as subtraction. And then we also learned that when you raise something to the power, you end up moving it to the front so that you can multiply that exponent times the number of logs. Change of base, we're going to learn this. 1 to 1, that's pretty easy. We started learning about that last week. Remember, if the bases are the same, then they cancel, and you're just left with m is equal to n, which makes our life easy. If you have an exponent, remember you have log base b, so that just leaves the exponent, and in this case the exponent is m. So if you have the log of b, if the base and the number that are inside the parentheses are the same, then your exponent just drops down to the bottom. Same thing with this one. If you have b as if your base is the same thing as your exponent, you can just cancel that out and you're left with just the m. Okay, let's see what that looks like in some examples. If I look at A, one of the rules that we learned is that if we multiply two numbers together, it's the same thing as adding them. So if you look at A, how can I rewrite 100 given the information that we have? Well, I know that if I square 10, so log base 13 of 10 squared will give me 100. So what I'm going to do is, according to this property here, I'm going to take my power, I'm going to move it to the front. So now I have 2 times log base 13 of 10. Do we know what log base 13 of 10 is? Yes, we do. We know that log base 13 of 10 is actually equal to 0.98 approximately. So now you're going to actually multiply 2 times that number, which using your calculator gives you 1.796. That is one way of looking at this problem. So take out a separate sheet of paper, and on here we're going to do some additional ways to solve A. Usually in math there's always more than one right way to do things. So you can put log base 13 of 100 is the same thing as if I were to do log base 13 of 10 plus log base 13 of 10. Because I know that this is the same thing as log base 13 of 10 times 10, which is just log base 13 of 100. Do we know what log base 13 is? Yes, 0.898. Do we know what log base 13 is? Yes, times 2 twice, or adding them together, you're going to get 1.796, which is the same thing as multiplying 2 times 0.898. Okay, let's look at B. B says 120. I know that 12 times 10 is 120, so I'm going to rewrite that as log base 13 of 12 plus log base 13 of 10. I know that if I'm adding these two log functions together, It's actually the same thing as if I were to multiply 12 times 10, which is actually log base 13 of 120. So since I know that, I know that log base 13 of 12 is, and I know what log base 13 of 10 is. I went ahead and whited out that what I wrote and brought it down a little bit further so that I could squeeze in the actual value of log base 13 of 12 and log base 13 of 10. So we know that log base 13 of 12 is 0.969, and we also know that log base 13 of 10 is 0.898. You're going to add these two together, and your final answer is 1.867. Okay, we're going to skip C and D. Go ahead and go to example 2. On example 2, we're going to look at some problems that have different bases. So I need the bases to be the same. Remember, it's like playing Tetris. We need the bases to be equal. So how can I rewrite 25 as a base of 5? If you said 5 squared, that is correct. Okay, 5 squared is the same thing as 25, and now I have the same base. Everything else is going to stay the same, 3x plus 1 in the exponent, and x minus 4 in the exponent. Okay, I'm just put some parentheses around it so that you can see the difference. But I can't just leave it like that. I've actually got to distribute the 2 to each of the terms. So I'm going to multiply 2 times x and 2 times a negative 4. So now we have 5 squared, which is just 25, but 2 times x gives us 2x, and 2 times a negative 4 gives us negative 8. On the other side, everything else stays the same. The bases are the same, so they can cancel, and now I'm left with 2x minus 8 is equal to 3x plus 1. Now, it's a little squished in there, okay, so I'm just going to keep going downhill. And we're going to have to probably do the next problem on our own sheet of paper. So you're going to subtract 2 x's from both sides because you want to get the x's on the same side. And you're left with 0 on this side. Minus 8 is equal to 3x minus 1 minus 2x is 1x plus 1. But you're not done there yet because you need solving for x, and x needs to be by itself. So on this side, the 1 and the negative 1 cancel, and you're left with 1x is equal to negative 8 minus 1 is equal to a negative 9. That was for problem A. Let's look at C. The bases are the same because remember, if there has no base written, you can automatically assume that it's 10. So natural log base of 10 and natural log base of 10 on both sides cancel each other out until you're just left with 2x minus 3 and 3x minus 8. You have to solve for x, just like we did for this side. We need to subtract 2 x's from both sides, and you're left with negative 3 is equal to 1x minus 8. But I can't leave the minus 8 on that side because I got to get rid of it. I got to get 8, x by itself, so I'm going to do the opposite, which is to add 8 to both sides. And negative 3 plus 8 is actually equal to, and I'm sorry that I ran out of space, but it's actually equal to 5 is equal to x. Okay, so that's C. Let's look at D. Log base 4 is on both sides. Log base 4 is on both sides, so we can just cancel out the log base 4, and I'm left with x squared minus 6 is equal to 10. Well, I need to solve for x. You're going to add 6 to both sides. You're left with x squared is equal to 16. You don't want to leave the x squared, so how do we get rid of the squared? That's right, we have to take the square root. Whatever you do to one side, you have to do to the other. The squared and the square root, they cancel each other out. So now you're just left with x is equal to, what's the square root of 16? That's right, 4 plus n minus 4. Okay, we're going to go ahead and skip B. I guess I should just slash it. Okay, let's go to example 3. So we're going to look at these properties really quickly and try to figure out why they work. If I take log base b of the same number, my log base b cancels, my exponents comes down to the bottom, and I'm just left with m. Look on the other side, same principle is true. If I take the exponent of something with the same base, disappears, and I'm just left with m. Okay, so we're going to apply these rules to example A. In this case, are the bases the same? The base and the number, they don't look the same, but what is 3 squared? 3 squared is the same thing as 9. So log base 9 to the power of x. 3 squared is 9. Now I have log base 9 of 9. So my final answer is just x. You look at B, log base 2 of 16. Can I rewrite 16 so that it's a power of 2? Well, 2 squared gives me 2 times 2, so that's not good. That's just 4. 2 to the power of 3 is 2 times 2, which is 4. 4 times 2 is 8. Let's try one more time. 8 times 2 is 16. So I can write this as log base 2 of 2 to the power of 4 times x. Now that I have the same bases, they can cancel each other out, and I'm left with 4x as my final answer. Let's look at D. Here we have the same base and the same exponent, so my final answer is just x to the power of 3. Here we have a 3 and the exponent is log base 3. I like this. It's log base 3 and 3, but I don't like this 2 in the front, so I'm going to bring it over here. The next thing that you have is 3 raised to the power of log base 3 of x squared. Your base and your power are the same, so you're just left with x squared. Okay, and then the very last one, f 125, I need to write it as the base of 5. So 5 squared gives me 25. 5 cubed gives me 125. Yay! So that was easy. So I'm going to have 5 to the power of 3 gives me 125, but I still have log base 5 of 2 to the power of x. We don't like this 3 hanging out in the front, so we're going to move it over to be an exponent. You actually have 5 to the power of 5 times 2x cubed. You now have the bases and the exponents the same, so you're just left with 2x cubed. 2x cubed is the same thing as 2x times 2x times 2x. 2 times 2 is 4, 4 times 2 is 8, so I'm actually left with 8x to the power of 1, 2, 3, to the power of 3. Okay, our last example, example 4, is using the change of base property. So if I have this property, it means I can change my base so that it looks like this. Okay, it's actually a division problem. Well, I know, and you guys learned, that I could rewrite this as a log function. You're going to write log base 5, and then you're going to go in a circle. Log base 5 of 9 is actually equal to x. So we need to figure out what x is equal to. And according to this rule, if you have log base b of m, that's the same thing as dividing the log of the number divided by log of the base. So I'm going to say that this is equal to log of 9 divided by log of whatever my base is, which in this case is 5. Do we know what log of 9 is? Yes, according to our table, we know